In this video lecture, we will see how to convert a binary number to its decimal equivalent. Let us take the first example in which we have to convert the number 10111 from binary to its decimal equivalent. Now the first step in doing this conversion is to identify the least significant bit and the most significant bit. So our given number is 10111. Now the rightmost bit is the least significant bit because it has the smallest weight. The bit at the extreme left, that is this one, is our most significant bit because it has the highest weight. Now, having done this, we will first make a table of 3 rows. Our first row contains the powers of 2. Here, we have started from the right. We start with the powers of 2. So 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, and we go up to 2 raised to 7. Now, for this particular problem, we will not require up to 2 raised to 7, but this is a general explanation which can be used for any problem which involves up to 8 bits. Now, in the next row, we write down the values of these powers of 2. So 2 raised to 0 we know is 1, 2 raised to 1 is 2, 2 raised to 2, 4, 2 raised to 3, 8, and like this, we have 2 raised to 7 is 128. Now, the third row, we will have the bits. Now, let us observe how to fill up this bits row. Starting from the least significant bit, we will start from the least significant bit, and that is why this has been highlighted here. What we will do is we will write each bit below the corresponding power of 2. So as we said, this is the least significant bit which has the smallest weight. So we will write this bit under the power of 2, that is 2 raised to 0. So we bring this bit here 1. The next bit in our number is 1. This is the bit with the next higher power, and therefore we now bring this bit to 2 raised to 1, that is 1. The next bit is again 1, that is copied under 2 raised to 2, that is the value 4. So this bit has the weight of 4. The next bit in our number is 0, which is written under 2 raised to 3. That means the value of this bit or the weight of this bit is 8. So we write 0. And the most significant bit, we put it here under 2 raised to 4, that is 16. So all our bits have been copied, and since there are no more bits left, we will just pad these remaining powers of 2 with zeros. Now all the bit positions have been allotted, and so our given binary number can be written as 0 into 128. Now this 0 is the bit at the extreme left. This we multiply it with 128. So this is 0 into 128. Then similarly 0 into 64. This is 0 multiplied by 64. That gives us the next. Then 0 into 32. 0 into 32. Then plus 1 into 16. So we have the bit 1 multiplied by its weight 16. 0 into the weight 8. 0 into the weight 8. So at each position what we are doing is we are multiplying the bit, that is say this bit, with the appropriate power of 2 or the value. So 1 into 4, so that is 1 into 4. Then we have the next bit 1 into 2, so 1 into 2, and the last bit is 1. We multiply it by its weight 1, so that is 1 into 1, and therefore this becomes 0 into 128, that is 0, plus 0 into 64, 0, and like this we have 1 into 16, you can observe, is 16, 1 into 4 is 4, and therefore we have the given binary number as a sum of these values, and this can be written as 0001, 0111 of binary is equivalent to 223 of the decimal. So these 3 zeros that we see here at the extreme left, these have been padded to create an 8-bit binary number. So these were not really necessary, but in case we come across an example where 8 bits have to be used, then we know that we must go up to 2 raised to 7. Let us take the next example where we have to convert the binary number 10010 to its decimal equivalent. Again, the steps will be similar. First, we identify the least significant bit. So 10010, this becomes the least significant bit, the bit which is at the extreme right. So this is the bit which is at the right, and we have the most significant bit, that is the bit at the left. So we have identified the bits. Again, as in the previous example, we make a table of 3 rows. The first row is powers of 2. So starting from the right, we have the powers of 2, 2 raised to 0, 2 raised to 1, 2 raised to 2, and like this we go up to 2 raised to 7. Below that, in the next row, we write down the values of these powers. So 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8, and so we have up to this 2 raised to 7 is 128. Now again in this, the third row will contain the bits. So we will pick up each bit starting from the least significant bit and put it below the appropriate power of 2. So since this is the least significant bit, it has the smallest weight, we copy this bit under 2 raised to 0, so that is 0. The next bit is 1, so we copy this bit under the power of 2 raised to 1. Our next bit is 0, that will be copied under the power of 2 raised to 2, that is the value 4. The next bit I have here is 0, so we copy it under the power 2 raised to 3 with value 8. And the last bit, the most significant bit in this example is 1, so that is copied under 2 raised to 4, and that becomes 1. Since all the bits have been used up, we just pad the remaining bits with 0. And again, in this example, our number is 0001010. It's the same number, but we have padded these 3 extra bits. These are the 3 extra bits. So you have 000, that explains these 3 bits, followed by 10010. Those are the remaining bits. This is equivalent to, now let us see, we again multiply each bit with the corresponding value. So 0 into 128 plus we'll have 0 into 64 plus we have 0 into 32 plus 1 into 16 plus 0 into 8 plus 0 into 4 plus 1 into 2 plus the 0 into 1. So we are multiplying each bit with the appropriate power of 2, and this can be written as 0 into 128 is 0, 0 into 64 0, 0 into 32 0, 1 into 16 is 16, plus 0 into 8 is 0, plus 0 into 4 is 0, plus 1 into 2 is 2, and plus 0 into 1 is 0, and this is equivalent to 18 of decimal. So this is how we can convert a given binary number to its decimal equivalent. Now, here is an important observation about binary numbers. Let us take the examples we solved earlier. This was the first example, 10111, and we saw that its decimal equivalent is 23. The next example was 10010, and its decimal equivalent was 18. Now observe this. In the first example, the least significant bit was 1, and the equivalent decimal number was an odd integer. So we have an important result. If the least significant bit of your binary number is 1, then the equivalent decimal value will be an odd integer. Let us take the next example where our binary number was 10010. Here, the least significant bit was 0. The binary equivalent, the decimal equivalent of this was an even number, and therefore here is our result. If least significant bit is 0, then the equivalent decimal value is an even integer. Now this you will realize is somewhat similar to what happens in the decimal numbers. We know that any number which ends with 0, 2, 4, 6 or 8 is an even number. So for example, number like 12, 16 or maybe 24, 18, 30, all numbers ending with 2, 4, 6, 8 or 0 we say are even numbers. And if a number ends with 1, 3, 5, 7 or 9 is we say it's an odd number. So we'll have numbers like say 23 or 31, 45, 67 or 89. All such numbers we say are odd numbers. So in a similar way, the important result is numbers, binary numbers in which the least significant bit is 1. We say that the equivalent decimal value will be an odd integer. And if the binary number has the least significant bit as 0, then we'll say that the equivalent decimal value is an even integer. Now this result is important and it can be sometimes used to check our answer when we convert from a binary to decimal or from a decimal to binary. Let us now take up an example of what happens with fractional binary numbers, fractional decimal numbers, decimal numbers which have a value less than 10. Now, let us consider a number such as 0.142 in the decimal system. Now, this number can be broken up as a sum of three parts. So, we have 0.1 plus 0.04 plus 0.02. So, we can see that this can be broken up into 0.1 plus 0.04 plus 0.002. Now, this part can be written as 0.142 can be written as 1 upon 10. So 0.1 is 1 upon 10. 0.04 can be written as 4 upon 100 and 0.002 can be written as 2 upon 1000. That means we can write 0.142 as 1 into 10 raised to minus 1. So you have 1 upon 10. When the 10 is taken up in the numerator, we have 1 into 10 raised to the power minus 1 plus 4 into the power 10 raised to minus 2 plus 2 into the power 10 raised to minus 3. So the important result here is that any number less than 1 can be written as a sum of the products of the digit and the appropriate multiplier of 10. So since this is the first place, 1 into 10 raised to minus 1. Since 4 appears in the second place after the decimal point, we have 4 into 10 raised to minus 2. Since 2 appears in the third place after the decimal point, we have 2 into 10 raised to the power minus 3. Now this result we will use it when we convert a fractional binary number to its decimal equivalent. Let us take this example of converting the binary number 0.1101 to its decimal equivalent. Now, just as in the previous case where we were dealing with decimal number, we can write 0.1101 as 1 into 2 raised to minus 1. Why we take 2 raised to minus 1? Because since we are dealing with the binary number system, this will become 1 multiplied by the base of this number system is 2. So 2 into 2 raised to minus 1 because this is the first decimal place. Then we have plus 1 into 2 raised to minus 2. So why 2 raised to minus 2 we take here? Because this 1 appears in the second position after the decimal place. So 1 into 2 raised to minus 2. The next digit we have here, the next bit we have here is 0. So this will become 0 into 2 raised to minus 3. The next bit that we have here is a 1. So we have 1 into 2 raised to the power minus 4. And therefore, now this example is dealing with the uh, fractional values of a binary number. Now we can observe one thing, that this 0.1101, if we write this number, then this point 1, the bit 1 here becomes the most significant bit, whereas the bit 1 here is the least significant bit. And therefore we now again make the table of powers of 2, the value and the bit. Only now the difference is when we make the power of 2, as we go from left to right, the powers of 2 keep on decreasing. So we have 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, 2 raised to minus 4, and so till we have 2 raised to minus 7. The values of these powers, 2 raised to minus 1 is 0.5, 2 raised to minus 2 is 0.25, 2 raised to minus 3 is 0.125, etc. till we have 2 raised to minus 7. Now let us observe. We take each bit from our fractional number. So starting from the most significant bit. We put the bit under the appropriate power of 2. So we have 0.1. So the bit is 1. So we put the bit 1 under the power of 2 raised to minus 1. The next bit is 1. This bit is written under the power of 2 raised to minus 2. The next bit, that means the bit in the third position after the decimal point, we put it as under the power of 2 raised to minus 3. The fourth bit after the decimal point, we put it under the power of 2 raised to minus 4. And since there are no more bits, we just put these bit positions as we put these bit values as 0. And therefore our given number 0.1101 can be written as equal to 1 into 2 raised to minus 1 plus 1 into 2 raised to minus 2 plus 0 into 2 raised to minus 3. Here it is, we can see this, plus 1 into 2 raised to minus 4, etc. And therefore this can be written as equal to 1 into 2 raised to minus 1 is 0.5, so 1 into 0.5 plus 1 into 0.25 plus 0 into 0.125 is 0 plus 1 into 0.0625 and this 0 into 0.03125 0 plus the next number also will be 0 and the last 0 into this also gives us 0, and when we add this we get 0.5 plus 0.25 plus 0.0625, that gives us 0.8125, and therefore the given decimal number in binary can be written as 0.8125 of the decimal system. Now let us see how to convert a binary number like 10111.1101 to its decimal equivalent. We'll observe that this binary number has an integer part, that is before the decimal, so it has an integer part, and it also has a fractional part, or it has also got a part after the binary point. So this we can say is its fractional part after the binary point. Now to convert this type of a number into its decimal equivalent, we first take the integer part, that means the part before the binary point, and we convert this number into its equivalent decimal. So this we already seen in the first example, how we convert an integral binary number into its decimal equivalent. Then we take the fractional part 0.1101. So we have the fractional part, or the part after the decimal, after the binary point, and we convert it into its equivalent decimal. So we saw in the earlier example that this is 0.8125, and therefore the entire number can be written as the integer part which corresponds to 23, and then the fractional part of binary corresponds to 0.8125. This becomes our complete equivalent value in the decimal system.